Today, we introduce the efficient coding principle and its formulation. This covers section 3.1 to 3.4 of the book. Would you like to find out the answers to the questions such as these? Why do retinal ganglion cells have centers around receptive fields? Why do these receptive fields increase their sizes in dim light conditions? Why should the contrast sensitivity function take its particular form? What is the optimal distribution of cones on the retina? And how should this depend on the characteristics of eye movements? Why does the contrast sensitivity for chromatic inputs suppress higher spatial frequencies more than that for luminance inputs? Why are color-selective V1 neurons less sensitive to motion signals? How can we predict the ocular dominance properties of V1 neurons from developmental conditions? Why are some V1 neurons double opponent in space and color, while retinal ganglion cells are not double opponent? Is there a principled way to answer such questions? The efficient coding principle could give this way. All these questions concern various forms of transform K from various visual input signals S to give outputs O. For example, when S are the visual inputs to the photoreceptors, O are the responses from retinal ganglion cells, then K is the receptive fields of these ganglion cells, and the efficient coding principle then leads us to the answers to these top three questions. Let me describe a general gist of this approach. The raw input S is often represented inefficiently and contains input noise. The encoding step introduces additional noise, leading to the total noise at the output. One can quantify how much information the output O contains about input S, and this information amount is denoted as IOS. The encoding is constrained by limited resources. For example, the dynamic range of O is limited, so IOS is a limited quantity. The idea is to optimize this transform K so that this quantity IOS is maximized. When this is done, the output O is set to form an efficient representation of the input S. As a result, K is often manifested as gain controls, causing decorrelation of the output channels when the input signal to noise is high, or smoothing out noise when the input signal noise is low. Applying this approach to various examples to get the optimal transform K will lead us, hopefully, towards the answers to the questions above and many other questions. We can compare the predictions from the efficient coding principle with experimental data to see whether this hypothesis makes sense, and to test this hypothesis to see where it works and where it fails. Before we do that, let's start with a quick introduction of what IOS is, and so therefore a brief introduction to information theory.